Something is afoot in our expanding cosmos. Nearly a century ago, the astronomer Edwin Hubble discovered the balloon-like inflation of the universe and the accelerating rush of all galaxies away from each other following that expansion. Backward in time led to our current best understanding of how everything began, the Big Bang. However, over the past decade, an alarming hole has been growing in this picture. Depending on where astronomers look, the rate of the universe's expansion, a value called the Hubble constant, varies significantly. Now, more than 2 years after its launch, the James Webb Space Telescope has cemented the discrepancy with stunningly precise new observations that threaten to upend the standard model of cosmology. According to Adam Rees, a professor of astronomy at Johns Hopkins University who led the team that made the new James Webb measurements, it's a disagreement that has to make us wonder if we really do understand the composition of the universe and the physics of the universe. On this, many cosmologists can agree. It started with a bang. Then, in an instant, the young cosmos was formed, an expanding, roiling plasma broth of matter and antimatter particles that popped into existence only to annihilate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma mirror should have consumed each other entirely. But scientists believe that some unknown imbalance enabled more matter than antimatter to be produced, saving the universe from immediate self-destruction. Gravity compressed the plasma pockets, squeezing and heating the matter so that sound waves, traveling just over half the speed of light, created acoustic oscillations that rippled across their surface. Meanwhile, the high-energy density of the early universe's crowded contents stretched spacetime, pulling a small fraction of this matter safely from the fray. As the universe inflated like a balloon, the standard story goes, ordinary matter, which interacts with light, congealed around clumps of invisible dark matter to create the first galaxies, connected together by a vast cosmic web. Initially, as the universe's contents spread out, its energy density and therefore its expansion rate decreased. But then, roughly 5 billion years ago, galaxies began to recede once more at an ever faster rate. The cause was another invisible and mysterious entity known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the stretching fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our cosmos grew, its overall matter density dropped while the dark energy density remained the same, gradually making the latter the biggest contributor to its overall expansion. Added together, the energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. They are also key ingredients in the lambda-cold dark matter, LCDM, model of cosmology, which maps the growth of the cosmos and predicts its end with matter eventually spreading so thin it experiences a heat death called the Big Freeze. Many of the model's predictions have been proven to be highly accurate. But here's where the problems begin. Despite much searching, astronomers have no clue what dark matter or dark energy are. As Ofer Lahav, a professor of astronomy at University College London who was involved in galaxy surveys of dark energy, said, "Most people agree that the universe's present composition is 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing fact is we don't understand the last two of them. But an even greater threat to the LCDM model has materialized. Depending on what method astrophysicists use, the universe appears to be growing at different rates, a disparity known as the Hubble tension. Methods that peer into the early universe show it expanding significantly faster than the LCDM predicts. Those methods have been vetted and verified by countless observations. Therefore, as Rees said, the only reason that I can understand at this point for them to disagree is that the model that we have between them is perhaps missing something. Measuring the universe's expansion takes a little bit more than a radar gun. The first method to measure this growth looks at the so-called cosmic microwave background, CMB, a relic of the universe's first light produced just 380,000 years after the Big Bang. The imprint can be seen across the entire sky, and it was mapped to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmic baby picture, the universe is almost entirely uniform, but hotter and colder patches where matter is more or less dense reveal where baryon acoustic oscillations made it clump as the universe exploded outward. This soap bubble structure ballooned into the cosmic web, a network of crisscrossing strands along whose intersections galaxies would be born. By studying these ripples with the Planck satellite, cosmologists inferred the amounts of regular matter and dark matter and a value for the cosmological constant or dark energy. Plugging these into the standard model spat out a Hubble constant of roughly 67 kilometers per second per megaparsec, MPC. Let's pause on this number for a moment. If a galaxy is at a distance of 1 MPC away from us, that means it will retreat from us and us from it at 67 kilometers per second. At 20 MPC, this recession grows to 1,340 kilometers per second and continues to grow exponentially from there onward. If a galaxy is any further than 4,475 MPC away, it will recede from us faster than the speed of light. A second method to find this expansion rate uses pulsating stars called Cepheid variables. Dying stars with helium gas outer layers that grow and shrink as they absorb and release the star's radiation, making them periodically flicker like distant signal lamps. In 1912, astronomer Henrietta Swan Leavitt found that the brighter a Cepheid was, the slower it would flicker, enabling astronomers to measure a star's absolute brightness and therefore gauge its distance. It was a landmark discovery that transformed Cepheids into abundant standard candles to measure the universe's immense scale. By stringing observations of pulsating Cepheids together, astronomers can construct cosmic distance ladders, with each rung taking them a step back into the past. It's one of the most accurate means that astronomers have today for measuring distances. To build a distance ladder, astronomers construct the first rung by choosing nearby Cepheids and cross-checking their distance based on pulsating light to that found by geometry. The next rungs are added using Cepheid readings alone. Then, astronomers look at the distances of the stars and supernovas on each rung and compare how much their light has been redshifted, stretched out to longer, redder wavelengths as the universe expands. This gives a precise measurement of the Hubble constant. In 2019, the method was used by Rees and his collaborators, who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was explosive. An impossibly high expansion rate of 74 kilometers per second per MPC when compared to the Planck measurement. Yet, Hubble lacked the necessary precision for the crowded regions of space the team was studying, causing some distant Cepheids to blur into neighboring stars. Dissenting cosmologists had some room left to argue that the result, however shocking, could have come from a measurement error. So when James Webb launched in December 2021, it was poised to either resolve the discrepancy or cement it. At 65 m wide, Webb's mirror is almost 3 times the size of Hubble's, which is just 2.4 m wide. Not only can James Webb detect objects 100 times fainter than Hubble can, but it is also far more sensitive in the infrared spectrum, enabling it to see in a broader range of wavelengths. By comparing Cepheids measured by James Webb in the galaxy NGC 4258 with bright type Ia supernovas, another standard candle because they all burst at the same absolute luminosity in remote galaxies, Rees and his colleagues arrived at a nearly identical result. 73 kilometers per second per MPC, including one made by Friedman with the Hubble Space Telescope on the rapid brightening of the most luminous tip of the red giant branch stars and another with light bent by the gravity of massive galaxies came back with respective results of 69.6 and 66.6 kilometers per second per MPC. A separate result using the bending of light also gave a value of 73 kilometers per second per MPC. Cosmologists were left reeling. According to Ryan Kassler, a cosmologist at the University of California, Merced, who has been working to explain the Hubble tension, the CMB temperature is measured at the level of 1% precision, and the Cepheid distance ladder measurement is getting close to 1%, so a difference of 7 kilometers per second, even though it's not very much, is very, very unlikely to be a random chance. There is something definite to explain. The new result leaves the answer wide open, splitting cosmologists into factions chasing staggeringly different solutions. Following the Hubble Space Telescope result, an official attempt to resolve the issue at a 2019 conference at the Kavli Institute for Theoretical Physics, KITP, in California only caused more frustration. As David Gross, former director of the KITP and Nobel laureate, said at the conference, "We wouldn't call it a tension or problem but rather a crisis. but how things can be fixed is unclear. Rees is pursuing a tweak to the LCDM model that would account for unknown physics and explain why the expansion rate appears to change when seen at different distances. But doing so would require dramatic changes to physics as we know it. One of the simpler solutions proposed by some cosmologists is the presence of an early period of inflation, where new exotic matter with properties similar to dark energy could have expanded in a second burst. Such particles could account for a surge in the early universe's expansion rate before promptly disappearing. The particles, however, remain undiscovered, and the hypothesized inflation period remains unverified. In response to this crisis, astronomers have called for a new measure of standard cosmology in the interim as new methods and experiments work to resolve it. But the Hubble tension is only the tip of the iceberg. As Wendy Friedman said, there are other anomalies that tell us maybe we're not just missing something about how the Cepheids are measured or how the cosmic microwave background is measured. These are telling us there might be something fundamentally missing from our picture of the universe, and it might have to do with new physics. One alternative approach to addressing these anomalies lies in reevaluating the nature of dark energy and dark matter. For instance, some theorists suggest that dark energy could vary over time and space rather than being a cosmological constant, implying it might have different properties in the early universe compared to today. Similarly, modifications to general relativity, such as adding extra dimensions or changing the theory's equations on cosmic scales, are also being explored. These adjustments could potentially resolve the Hubble tension without resorting to unknown exotic particles. Another promising direction involves leveraging the upcoming generation of astronomical instruments. The Vera C. Rubin Observatory, set to begin operations soon, will conduct the Legacy Survey of Space and Time, LSST, mapping billions of galaxies and providing unprecedented data on cosmic structure. Additionally, the Euclid Space Telescope, planned for launch by the European Space Agency, aims to measure the universe's acceleration with high precision by observing distant galaxies and galaxy clusters. These next-generation observatories will help cross-check current measurements and may uncover new phenomena that offer insights into the underlying physics of the universe. In parallel, advancements in theoretical physics continue to push the boundaries of our understanding. The ongoing quest for a quantum theory of gravity, which seeks to reconcile general relativity with quantum mechanics, might provide clues that address the current cosmological discrepancies. Furthermore, collaborations between cosmologists and particle physicists could lead to new discoveries at the intersection of these fields, shedding light on the elusive nature of dark matter and dark energy. Ultimately, the journey to resolve the Hubble tension and other cosmological anomalies represents a convergence of observational prowess and theoretical ingenuity. As the scientific community navigates this uncharted territory, it remains a testament to the ever-evolving nature of our understanding of the cosmos. The discoveries and breakthroughs that lie ahead will not only reshape our view of the universe's expansion, but also deepen our comprehension of the fundamental forces that govern its destiny. The current state of cosmology presents a puzzle that challenges our fundamental understanding of the universe. Edwin Hubble's groundbreaking discoveries nearly a century ago laid the foundation for our understanding of cosmic expansion. The concept of the Big Bang emerged, explaining the universe's origin and subsequent inflation. However, recent observations have revealed discrepancies in our understanding, particularly concerning the rate of expansion known as the Hubble constant. Astronomers have long relied on the cosmic microwave background, CMB, and pulsating stars known as Cepheid variables to measure the universe's expansion. These methods have provided valuable insights into the composition and evolution of the cosmos. However, advancements in observational technology, such as the James Webb Space Telescope, have led to increasingly precise measurements, uncovering discrepancies between different observational techniques. The discrepancy in the Hubble constant has sparked intense debate within the scientific community. Some researchers advocate for modifications to the standard cosmological model to account for unknown physics, while others suggest revisiting the nature of dark energy and dark matter. These proposed solutions reflect the complexity of the challenge at hand and the need for interdisciplinary collaboration to unravel the mysteries of the universe. One intriguing possibility is the existence of an early period of inflation, during which exotic matter may have driven a rapid expansion of the universe. Such a scenario could explain the observed discrepancies in the expansion rate and shed light on the fundamental forces at play during the universe's infancy. However, this hypothesis remains speculative, and further observational evidence is needed to validate its validity. In addition to theoretical advancements, the next generation of astronomical instruments holds promise for resolving the Hubble tension. The Vera C. Rubin Observatory and the Euclid Space Telescope are poised to provide unprecedented insights into cosmic structure and acceleration. These instruments will complement existing observations and may offer new avenues for understanding the underlying physics of the universe. The quest to resolve the Hubble tension is emblematic of the scientific process, a continuous journey of discovery and refinement. As researchers grapple with the complexities of the cosmos, they remain guided by the principles of observation, experimentation, and theoretical reasoning. The resolution of this puzzle will not only deepen our understanding of the universe's expansion but also pave the way for new discoveries and insights into the nature of reality. At its core, cosmology is a quest to understand the fundamental nature of the universe. From the origins of the cosmos to its ultimate fate, cosmologists seek to unravel the mysteries that have captivated human curiosity for centuries. The journey is fraught with challenges and uncertainties, but it is also replete with opportunities for discovery and enlightenment. The resolution of the Hubble tension will require a concerted effort from the scientific community. It will necessitate collaboration across disciplines, from astronomy and physics to mathematics and computer science. By pooling resources and expertise, researchers can tackle the most pressing questions about the universe's expansion and evolution. As we venture into this new era of cosmological exploration, we are reminded of the profound interconnectedness of the cosmos. From the smallest subatomic particles to the largest galactic superstructures, the universe is a vast tapestry of interconnected phenomena. Each discovery brings us closer to unraveling its mysteries and understanding our place within it. In the face of uncertainty, scientists remain undeterred in their pursuit of knowledge. They are driven by a relentless curiosity and a deep-seated desire to unlock the secrets of the universe. The journey may be long and arduous, but it is also filled with moments of awe and wonder as we glimpse the majesty of the cosmos. Ultimately, the resolution of the Hubble tension will not only advance our scientific understanding, but also enrich our collective appreciation of the universe's beauty and complexity. It is a testament to the human spirit of exploration and discovery, a journey that transcends boundaries and unites us in our quest for knowledge.